This lecture is about the AR1 process, the autoregressive process of order 1. So here's the definition of AR1. I have a time series process going from Y1 to YT, and we will say that this process follows a stationary AR1 process if these Y1 through YT is a stationary process and YT is determined as follows. The value of Y at time t is equal to a constant beta 1 plus another constant rho times its value in the previous period plus epsilon t, where epsilon is an error term. Now we will focus our attention on stationary AR1 processes, even though it's possible for a process to follow a non-stationary AR1 process. So remember, it's stationary. YT has a constant expected value, a constant variance, and the covariance between YT and YT minus S will depend on S only and not T. You can view this as a linear regression model where the only explanatory variable is the lagged dependent variable, and where we have no other exogenous variables that explains YT. So Y at time t is determined solely by its value in the previous period plus some error term, or we can also call it a shock to YT in period t. Now, this is certainly the most important process in time series analysis, and we will carefully study its properties and how these properties depend on these two parameters, beta 1 and rho. But before that, let's have a closer look at the error terms epsilon t. We will assume in the AR1 process that these error terms follow something called a white noise process. So simply stated, the error process epsilon 1 through epsilon t is a white noise process if the following three conditions are satisfied. First of all, epsilon t must be independent of all lagged values of y. So the shock at time t affecting yt must be independent of the lagged value of y, as well as the value of y 2 periods back, and so on. Obviously, it's not going to be independent of yt, since yt is partly determined by this error term epsilon t. But the point here is that the previous value of the dependent variable yt minus 1, it will affect the value of yt today, but not the shock. Second, if you look at two distinct error terms, that is two error terms at two different points in time, they will be assumed to be independent. From this, it follows that this error process will be non-autocorrelated. No autocorrelation in the error process. And finally, the expected value of this shock or error term must be 0 for all time periods t, and the variance must be constant. We denote it by sigma square, so no heteroscedasticity. Note that we write these expected value and variances without conditioning on yt minus 1. And that's simply because of the second assumption. We made the assumption that they're independent. So you can also write the expected value of epsilon t conditionally on the lagged values of y. That will be 0 as well. So let's have a look at what data looks like if it follows an AR1 process. To do that, let's perform a simulation study where we can adjust beta 1 and rho and see what effect that will have on the AR1 process of y. Here is the AR1 process. We make the assumptions that the error terms are white noise, and I want to look at data where t goes from 1 to capital T. In the simulation study, I'll set capital T to 100. If we look at y1, how is the first value of y determined? Well, that's equal to beta 1 plus rho times y, and 1 minus 1 is 0, so y is 0 plus epsilon 1. So this is slightly problematic because no matter what we do, in order to determine y at time point t, I need to know y in the previous period. But to know y in the previous period, I need to know y one period before that, and so on. So it seems like we've ended up with a dilemma where we can never determine y. There is a neat solution to this problem where we just simply simulate y0 from a particular distribution. But more about that just a little bit later. First, let's look at the error terms. And the error terms has no such problem. They are going to be white noise. And to make them into white noise, I just simulate them. I can pick any distribution, but let's do the normal. So like this from the normal, and as the mean I must pick 0. That's a necessary condition for the error terms to be white noise. And second, I can pick whatever I like for the standard deviation. Let's pick something like 0.2. The only important point is that if I pick 0.2 in row 3, I must pick 0.2 in all other rows. Otherwise the error terms will be heteroscedastic and then it's not white noise. Like this. If I copy this down, I will have homoscedastic error terms, and these are now white noise. They are in no way determined by the y variables. They have a constant expected value, there is no autocorrelation, and there is no heteroscedasticity. So let's get rid of some decimals. I have simulated a value for y0 in cell F2, and let me get back to exactly how I have done that a little bit later. But once I have a value for y0, I can simulate the value for y1. Remember, y1 is beta 1 plus rho 0 plus rho times y0 plus epsilon 1. I've actually named these cells beta 1 and rho, so that makes it a little bit simpler. I can now just type beta 1 plus rho times, and here is the key point. I need now to refer to the y value in the previous period. And the y value in the previous period is just one row above. So right there, that is y0. And to this I just add the error term, which is in E3, and I have simulated my y1 value. Now if I just simply copy this one step down like this and look at the data, it says beta 1 plus rho times F3. F3 is the y value in time period 1, so it's y1 plus epsilon 4, and that's the error term in time period 2. And this is indeed how y2 should be determined, so this formula will be correct, and for the same reason, if I just copy this down, the formula will be correct all the way down. So now I have actually simulated data from an AR1 process, and we can have a look at what it looks like. I have added here the scatter plot of the y data as a function of t. I have time on this axis. Let's switch this because I only have time up to 100, so let's change this to 100. So this is indeed an example of an AR1 process. This is kind of a trivial and non-interesting AR1 process because beta 1 is 1, 0, and rho is 0. And if you look at the AR1 process, if I set this to 0 and this to 0, it just is that yt is equal to epsilon t. So yt here is just white noise. But there is an important lesson to learn from that, and that is that white noise is actually an AR1 process. If you like, a trivial AR1 process. So let's see what happens now when we change the parameters, and I will begin by changing rho to see what the consequences will be. The first thing we can notice is that when rho is equal to 0, then yt does not depend on yt minus 1. So when rho is equal to 0, the covariance between yt and yt minus 1 is 0, and there is no time dependence at all. In this case, we're actually looking at a random sample. If I increase rho, if rho is greater than 0, we can see that whenever yt minus 1 increases, because rho is positive, yt will increase. So in this case, the covariance between yt and yt minus 1 will be positive. And similarly, if rho is negative, this covariance will be negative. Remember that a positive covariance implies that we will observe cycles in the data. The argument for that is quite straightforward. Let's say I have a time series process yt, and the expected value of yt is equal to 0. But at a particular point t, I observe a y value that is positive. Well, due to this positive covariance, that will make it more likely for the y value in the next period to be positive as well. Even though the expected value of y is 0 in every time periods, due to the covariance being positive, the y value in the next periods will be positive as well. Well, not for sure, but at least there is a higher probability that it will be positive. The expected value is 0, so there is actually a tendency for this to go to 0. So it might look like this. And then when the y value becomes negative, for the same reason, it's more likely for the value in the next period to be negative as well. And that's why we observe cycles when there is a positive correlation between yt and yt minus 1. So let's investigate that to see if we can see these cycles. So I'm now going to increase rho, making the correlation between yt and yt minus 1 positive. So let's take it up to 0.5 first of all. It's not super clear, but it is actually clear that there is a positive correlation right now. For example, you have clusters of a whole bunch of positive values here, a whole bunch of negative values here, a whole bunch of positive values here. And that would not happen if this was a random sample and the covariance between yt and yt minus 1 was 0. If this was a random sample, then there will always be a 50-50 chance of being above 0 and below 0. And the probability of observing a whole bunch above 0, for example, would be very, very unlikely. Now, as I increase this value of rho, we can see that these cycles are becoming more and more clear. 0.8, for example. Now it's very obvious that this is not a random sample. take it up to 0.9, and let's go to 0.98. I will discuss in a second why 1, we can't go to 1 or above 1, come back to that, but 0.98, and the cycles are really obvious. If I F9 a couple of times here, we see that the cycles are extremely visible in the data. This is actually one of the reasons for why this AR1 process is so popular in economics, because it is able to generate cycles. And that is something that we often observe in economic data. For example, in the business cycles of growth rates and so on. So we have discovered that the rho parameter is a measure of the dependence between yt and yt minus 1. The bigger the rho, the bigger is the dependence. If rho is equal to 0, there is no dependence at all, and we just have white noise. We can actually also make rho negative, and that would introduce a negative covariance. A negative covariance would mean that whenever yt is bigger than 0, it's more likely for yt minus 1 to be less than 0. In order to see this, I've added lines between these points. So let's make this 0 minus 0.8, and we can clearly see this effect. So for example, y0 is negative, y1 is positive, y2 is negative, y3 is positive, and so on. So it keeps on sort of jumping up and down like this. Now, this is really, really uncommon to observe this type of behavior for economic data, and negative values for rho are really uncommon. Let's continue our investigation into the AR1 process by looking at the effect of beta 1. So I'm putting this back at 0, and let's remove these extra lines. So if I increase my beta 1, well, it is the intercept, so you're probably not going to be too surprised to see that if I increase beta 1 to 10, the whole data set will just move up and the intercept will be 10. Perhaps it will surprise you a little bit, the fact that if I now change the rho to 0.5, the intercept is actually no longer 10. It looks like it's 20, and that is in fact true. The expected value of yt in this case is 20. So it's not as simple as just claiming that beta 1 is the expected value of yt. The rho variable will also actually affect this intercept, or the expected value of y. But in general, it's okay to claim that beta 1 has an effect on the level of yt. It will affect the expected value of yt and the intercept of a trend line. So now that we know a little bit more about the AR1 process and the effects of the rho parameter and the beta 1 parameter, let's try to find the moments of yt. And by the moments we mean the expected value and the variance. Let's erase this for now and focus on the expected value. So let's see if we can figure this out, the expected value of yt. Remember, we have assumed that this is a stationary process, so the expected value of yt must be the same as the expected value of y for any other time period. It must be constant. Well, this is just the expected value of the right-hand side. And the expected value can go inside sums. So this is the expected value of beta 1. That's just a constant, so that's beta 1, plus expected value of rho times yt minus 1. Rho is a constant, so we can take it outside like this, plus the expected value of the error term. Well, that's 0 because we have assumed that the error terms form a white noise process, and those always have an expected value of 0. So plus 0 if you like. Now, if the process is stationary, this must be precisely the same as the expected value of yt. So I can take this entire part, move it to the left hand side, and it says expected value of yt minus, on this side I have rho times expected value of yt equal to beta 1. Let's factor out expected value of yt. 1 minus rho equal to beta 1. And let's divide both sides by 1 minus rho. So then I have the expected value of yt. It's beta 1 over 1 minus rho. So let's check if this is, or if it makes sense from using the simulation study. So let's add expected value of yt here, and according to the formula, is equal to beta 1 divided by 1 minus rho, like this. And according to the formula, the expected value of yt should be 20, and looking at the simulated data, that does seem to be perfectly correct. And this will work. Let's try other values. Let's do, let's say, 10 here and 0.9 here. Then the expected value will be 10 over 0.1, so 100. And yes, it does seem to be working fine. So one tiny issue here, and that is this formula. What would happen if rho is equal to 1? Well, in that case, the denominator is equal to 0, and you can't divide by 0. So it seems like we've hit kind of a dilemma here. How would we calculate the expected value of yt if rho was equal to 1? Well, it turns out that when rho is equal to 1, this process is actually not stationary. So if rho is equal to 1, then it's not stationary. This is really important, but it will also save us, because for non-stationary processes, there is no longer a claim that the expected value of yt should be constant. And in order to arrive at this equation, we made this assumption, remember, that the expected value of yt minus 1 should be expected value of yt. So if it's not stationary, this whole formula is pointless. Now, it turns out that when rho is equal to minus 1, then the same problem will actually appear. So it's not stationary here as well. We can see that also in the simulation study. The whole thing just goes nuts. If I try to do rho equal to 1, I just get a lot of div by 0, and the same for minus 1. So actually only values that are in between minus 1 and 1 will work. So we need to keep rho between minus 1 and 1 for the stationarity to be satisfied. And this is such an important condition that we give it a name. We call it the stability condition for the AR1 process. So let's summarize these ideas before we look at the moments of the stationary AR1 process. We've already found the expected value, but let's just then say that for an AR1 process to be stationary, a necessary condition is that it satisfies the stability condition. So the absolute value of rho must be less than or equal to 1. Then the AR1 process is stable, and only stable AR1 processes can be stationary. And of course, only stationary processes has a constant expected value and a constant variance. We have found the expected value. So if yt follows a stationary AR1 process, that is, we know that the stability condition is satisfied, and if the error process is white noise, and sigma square is the variance of the error term, then the expected value of yt is beta 1 over 1 minus rho, which we found. So let's look at the second moment. The second moment, the variance. And actually, that's pretty much just as simple. The variance of yt is equal to the variance yt is beta 1 plus rho yt minus 1 plus epsilon t. Now I can take the variance inside. The variance of a constant is just 0, so that's not going to do anything. Then I have the variance of this term. This is a constant, so I can take it outside if I square it. So it becomes rho square times the variance of yt minus 1 plus the variance of the error term. Well, we use the symbol sigma square for that. And notice that I can do this because I have assumed that these two are independent. And that's a requirement for this variance formula to work. Same type of argument. If my sequence is stationary, then this is the same as variance of yt. For a stationary process, the variance is constant over time. I do the same thing. I move this term over to the left-hand side. I can just factor variance of yt immediately. Then I have 1 minus rho square left. And on the right-hand side, I have sigma square. So dividing both sides, I see that the variance of my yt is sigma square 1 minus rho square. We also have stated in the presentation. So the standard deviation of yt is equal to sigma divided by square root of 1 minus rho square. In the simulation, I used sigma equal to 0.2, so divided by sqrt 1 minus rho squared. That's the standard deviation of yt. We can see that the standard deviation of yt, or the variance of yt, is as small as possible when rho is equal to 0. And as rho increases, the variance of yt and the standard deviation of yt increases. If I put this to 0.99, for example, then the standard deviation goes up a lot. And similarly to the expected value, we cannot set rho equal to 1, then the variance would not exist. So we can look at now the setting of y0. If we look at the formula for how I simulated y0, you can see that it's simulated from a normal distribution. It has expected value beta 1 over 1 minus rho, and it has standard deviation 0.2 over 1 minus rho square. So I have simulated y0 from a normal distribution with precisely this is my expected value and this as my standard deviation. Keeping rho between -1 and 1 strictly will then create a whole sequence of stationary observations for y. We sometimes say that we start the process at the stationary distribution, meaning that we simulate the starting of the process in such a way that it will have the correct expected value and variance. Now, even if I won't do it in this lecture, it's not hard to show that the covariance between yt and yt minus s is equal to rho to the s times the variance of yt. As you can see, the expression on the right hand side depends on s but not on t, and that's exactly what we need for stationarity. Also note that since rho is strictly between -1 and 1, rho to the s will become smaller and smaller as s increases. And that means that the covariance between yt and a lagged value of y, s periods back, will decrease as s increases. Again, for time series data, that is quite realistic. Two observations very far from each other in time ought to be less correlated than two observations which are close in time. So the final issue we will look at in this lecture is, so if I have data on y, and I assume that this data is from an AR1 process, is it then possible to estimate the parameters beta 1 and rho? And the answer is yes, you can do it using OLS, but since we have lag dependent variables, the Gauss-Markov assumptions as we have stated them simply cannot hold. The problem is the exogeneity assumption. It's possible to show that with lag dependent variables, the lag dependent variable cannot be exogenous. However, we can typically make another assumption, an assumption called predeterminedness, which will at least make your estimates consistent. However, you can actually show that even though the explanatory variable, which is the lag dependent variable in this case, is not exogenous, it will still be the case that as long as the errors are white noise and the process is stationary, then the OLS estimator will be consistent, and the standard error estimates will be consistent as well. In this particular case, with the independence between the error term and lagged values of y, an assumption called predeterminedness can hold, and that's actually enough to show consistency. But because the Gauss-Markov assumption is violated, the estimator will not necessarily be unbiased. And it's actually possible to show that it will be biased towards 0 in this case. But the bias will become smaller and smaller as the sample size increases and eventually disappear.